Okay, so I guess we'll start now and see if more people join us. For now, I'm going to start with a little recap, so we'll have time for people and so on. So today I'm going to cover, hopefully going to completely cover these two topics. It's unclear, depends on how fast we go, but if not, I'll use a little bit of tomorrow's time to finish. And so today I want to, well, I'll start by recalling what we did last time and the lessons that we learned. And then I'll use that to motivate this algebraic approach to quantum field theory, where you really consider that the algebra is something fundamental, and you can put states on that algebra that simply map algebra elements to complex numbers. And then you can find a procedure to represent all that in terms of Hilbert space and operators on Hilbert space in the usual quantum field theoretic setting and quantum mechanical setting that we're used to. And then I'm going to look at states, and I'm going to, I'm going to focus on physical states, which are states called Hadamard, or states that satisfy the Hadamard property. And I'll show you how that property is important for the renormalization of the stress energy tensor of a field theory, for quantum field theory, which is of course a very important observable if you want to go on and do semi-classical gravity, if you're a very brave person, because it's quite convoluted, as we will see. So, I mean, just some references. Some references for you and to go and read if you want to further what I'm talking about here. And so for algebraic quantum field theory, very good exposition is this. Fuster's Max Planck's lectures from 2008. And there's also very, careful exposition by Benini and Appiaggi in this compendium of edited by Brunetti, Appiaggi, Fredenhagen, and Ingvason from 2015. It's a thick book that contains many topics on algebraic quantum field theory, from elementary to quite advanced. And this chapter covers this algebraic quantization story. Quite some detail. They use a minus plus 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 signature in both these cases, so be aware of that. It's different to the convention that we're using, but since everything is very constructive and so on, it doesn't really matter. It's not a big deal. And then for states, I really recommend you to read some pieces of K and Wald. K and Wald is a very long paper, very famous long paper, which introduces the rigorous definition of the Hadamard property for the first time in the way that we're going to see it, because there's a modern formulation in terms of micro-local analysis that we will not cover. because it's using modern mathematics. It's quite, it requires a lot more technical mathematics and skills. We will not cover it. So this is very, very good, very clear sports paper. Then there's this Kafkin and Moretti, which is again a chapter in this same Dappiaggi and so on editors, which is again very precise and detailed. Then for renormalization of the stress energy tensor, I advise you to have a look at Wald 1978, also a very famous paper where he introduces the Wald axioms for renormalizing the stress energy tensor. We'll see what that is. And also, Wald's little red book gives a very good account of this story. And finally, these two, at least these two, actually this one as well, and I think all of these deal with 4 dimensions. So they do renormalization of stress energy tensor in 4 dimensions and the Hadamard property in 4 dimensions. And this one does it in n dimensions from n onwards. Okay, so if you want to have a look at that. I'll just focus in 4 dimensions, but the idea is the same. Okay, so let's start by recalling. So recall that last time we made a construction. In fact, we made one construction for the Fulling-Winkler vacuum, but we had already constructed the Minkowski vacuum in the first little lecture that we had. And so the story was the following. So you can go to Minkowski space, right, which I'm going to draw here, and construct a Minkowski vacuum based on a theory which uses time evolution with respect to this Killing vector dt in the standard Minkowski coordinates, and has a Hilbert space that has positive frequency modes with respect to that time. Right? And so the field solutions we learned look a little bit like this. So this is a measure that we have written explicitly before. Okay. Has some creation operators here. Some annihilation operators, sorry, and some perhaps it has a little peaking there. So that's really what we're referring to, like in a sense it's a wave package, you see, centered around some momentum, some preferential momentum, and then some X contributions. Okay, and we also saw that if you restrict yourself to this region, you can consider Ringler space. Okay, which is also a flat space-time. This is what we did last time. Okay, yeah. And you can construct a vacuum which is called the Ringler-Fulling vacuum with respect to another Killing vector, let's say tilde, which is equal to d eta. Okay, construct a Hilbert space which has elements that are of positive frequency with respect to this notion of time. And you can write fields, quantum fields, as in the following way, right? Tilde lambda plus cc, okay? Where these two are different. This is an annihilation operator acting on the Fock space in this theory. This is an annihilation operator acting on the Fock space of this theory. And we saw that the two theories are not unitarily equivalent. and that the notion of particle is quite different, and that the Hamiltonian of one theory and the Hamiltonian of the other theory are quite different. They're based on, you can write them in terms of different creation-relation operators, and that say the vacuum expectation value of this Hamiltonian with respect to the Minkowski vacuum looks thermal. Okay, it looks like it's thermally like the state is thermally populated, as far as you can read from here. So the two theories are quite different. However, we've also seen that the canonical commutation relations, okay, so, and then this one for phi, and for pp is not. So the canonical commutation relations, say for Minkowski, and in the case of the Ringler-Fulling vacuum, so viewing these operators as acting on a Hilbert space defined by so let me call this unit here, this is equal there, and this is a suitable, there's a suitable integration measure here. What do we want to put? Okay, and we've seen that the form of the commutation relations, when we view the field as operators acting on the field and the momentum as operators acting on this space, and when we view them as fields and momentum as operators acting on that space, so represented in one or the other space, have the same form. So we have seen that in some sense the commutation relations are quite important. They have a lot of information about the field theory, and in fact we can imagine, and this is what we will do in the future, this is what we will do today, we can imagine that the commutation relations, the field equation, and a few other things define what a quantum field theory is for the Klein-Gordon field. And then we will find a way to manufacture some Hilbert space on which they can be represented as operators, these observables, right? Okay. And yeah, so let me take it from there. Just this is what we've done so far, right? Okay. So I want to remind you that we will deal. So from now on, I'm going to be on an arbitrary space-time. I'm not going to be Minkowski or Ringler or anything like that. I'm going to go to an arbitrary globally hyperbolic space-time. Which I will also assume that is orientable and time-orientable, as we saw in the first class, first little lecture. And
are you going to assume that this spacetime is solution of the Einstein field equation, or it is not necessary?
Well, in principle, you don't have to for the construction, but in practice you would like it to be. Okay. I mean, the construction is geometric and doesn't care so much about that, but okay. And I want to start by going back to classical field theory, right? I want to start by thinking of how we characterize the solution space of classical field theory. So, if we are in a globally hyperbolic space-time, we know that we have a well-posed problem that we can define on some surface sigma, where we can put some initial data for the field. And then we know that out of that initial data and the field equations, we can get solutions that propagate causally, because these are relativistic field equations, so the field propagates in a Poisson way. Okay. And so, if we're trying to solve the Klein-Gordon equation, there's no gauge or anything that complicates things, and we can very easily associate, or I classify the solution space by initial data. Initial data that we put in sigma. And I'm going to imagine that I'm putting initial data of compact support. In Minkowski, we can put initial data just that decays in a sufficiently fast way, so like Schwarz functions or something like that, but I will now focus on initial data of compact support from now on. Okay? So we can put some initial data, and we can characterize the solution space by initial data. So namely, if I give you the initial value of the field and its velocity, then you know how to give me the solution by solving the Einstein, the Klein-Gordon equation. Okay, that's the idea. And we know that observables, right? Observables are maps from the solution space to R. This is what we have learned. Okay, and we had those, if you remember, we had those Poisson brackets that we introduced with the help of a complex structure in the first class, in the first lecture. Okay, so this space carries a symplectic. This is symplectic space, and this carries a Poisson structure. Poisson structure. Okay. And now I want to take the point of view, because when we're in arbitrary spacetimes, it's you know, the Klein-Gordon equation doesn't care about the symmetries of the spacetime. So the way in which we have solved the Klein-Gordon equation before is we had a lot of symmetry. We could decompose the field into in this harmonic form in the t variable, in a time variable, and we used that symmetry to solve the problem, and we got these nice solutions. But in general, you don't have that symmetry, and you don't have a natural notion of a Hamiltonian that you can associate in the quantum realm to that symmetry. But you still have the Klein-Gordon equation that gives you solutions, you know, throughout space-time. And so, in a sense, in curved space-time, what is more natural is to think of the solution space as field configurations themselves, okay? So, in particular, I want to consider that the solution space I. I'll tell you what this is in a minute. That lie in the kernel of the Klein-Gordon operator. Okay, so what do I mean by that? The Klein-Gordon operator is equal to that's the Klein-Gordon operator. And so when I say that the solution space lies in the kernel of that operator, I mean that that's equal to 0. So meaning I'm on shell, right? This is just saying that you're satisfying the field equation. And what does that mean? That means a spatially compact smooth functions on space-time. Okay. So what that means is, well, consider this region here. This region is spatially compact. Why? Because it doesn't extend to infinity in the spatial direction. So whatever slice I take, it's compact in that direction. So let me give you, so that's just intuition. Let me give you the definition of what spatially compact is. So just a little, maybe I'll write it here. A mini definition. Okay. F is the spatially compact smooth function if the support of F is inside Jk, where J is, if you remember from our notation, I think I introduced these two guys. So the causal future and the causal past of K. Okay, where K is a subset of M, but it's compact. It's compact. Okay. So how does this tie in with our intuition? Well, let's again look at a function that has support here, for example. And if I draw a K, if I draw some K here, then of course that's J of K. That's J of K. And this lies inside of that bigger region of space-time. Okay, so that's the idea. Okay. So I'm not going to make it so confusing. Let's try not to make it so confusing. I have sigma. I have the support of initial data here. Let's say support of initial data, phi and phi dot. Okay. Line surface. And then I have the solutions that have supported on this region, and it's spatially compact support. Okay. So the solution space, when I consider initial data of compact support, is smooth functions of spatially compact support that are in the kernel of the Klein-Gordon operator. Okay, that's the space of solutions.
The box is just
the D'Alembert.
Yeah, but in that with that metric, right?
Yes, yes, of course. So this is GAB. Yes. Okay. Right. And of course, I want to eventually write some phase space that has observables that go from the solutions to R, and I want to introduce a Poisson bracket. Okay. That's the idea. I want to, instead of looking at things from this canonical perspective where I have initial data and I have a Poisson bracket on the space of observables, so of momentum position and other observables in here. I want to do it covariantly, so I want to have a Poisson bracket on maps from the covariant solution space or configuration space to R. Right? I want to put a Poisson bracket here. Okay. So that's going to be a bit the game that we're going to play now. Right. To do that, let me introduce the notion of a normally hyperbolic operator. Okay. So we call P, and I'm going to give a non-definition. I'm going to give something that is not the definition but captures the idea of the definition. So P is a normally hyperbolic operator if I choose local coordinates. Okay, if I choose some coordinates such that P looks like this. P acting on some function where it acts. It doesn't necessarily have to be the Klein-Gordon field, it could be something else. But in a particular case, of course we are concerned about, we are thinking in the back of our heads about the Klein-Gordon equation. But this definition is, let's say, more general than that. Okay. So, P is a normally hyperbolic operator if I choose some coordinates and it looks like that. Okay. So in particular, the Klein-Gordon operator, if I decide to disentangle all of this expression, it'll have that form. And in here, I want to say that this is the inverse metric. This is just some smooth vector, and this is a smooth function. Okay? So everything is smooth in here. Right? And let me just write a mini remark that the actual definition is the above statement made geometric. So it's a geometric version of that statement. In other words, we need to think about fields on some manifold as locally looking like sections on some bundle. So for example, if I think of a Klein-Gordon field, it locally looks, you can look at it in general like a section in the real bundle. So in other words, I take M and I attach fibers that are all the real line, right? So that's the real bundle. And of course, I can look at it, I can look at the field as sections in that bundle, in the sense that if that they invert the projection operator. So right? So if I do section and then project, I go back to the same point. It's just locally. Okay, that's the idea. Well, in general, in some vector bundle or something like that, it will not be some general crazy bundle. But that's all right. It could be some principal bundle or something like that, you know. But that's the idea. So. So then I choose a local trivialization in the bundle and I use some coordinates here and I express the field locally as some functions, right? In some space-time region.
Is it psi on the right hand side?
Yes. Yeah. Okay. So that's a non-definition of a normally hyperbolic operator. Now I want to give you a definition of another thing, which is going to be a proper definition, hopefully, of a green hyperbolic operator. Okay, so let me define this. So let M be globally hyperbolic. So remember, globally hyperbolic means that there exists a Cauchy surface, and that if I put, typically for field equations, if I put data on this Cauchy surface, I can solve them. Right? Maybe I have to do some tricks with gauge theories, but that's fine. Okay? Okay, and now let me introduce an operator P. So let P is an operator that goes from smooth functions to smooth functions. And it's a linear hyperbolic. Partial differential operator. Okay? So the Klein-Gordon field is one example of a linear hyperbolic partial differential operator. Okay. So for example, Klein-Gordon. Now I'm going to define some maps. Which go from smooth functions of compact support in M to smooth functions in M. And they are called advanced and retarded green operators. Green operators of P. Okay. If the following points hold, me tell you what those points are. First of all, right. For F, compact support and smooth, we have that P plus minus F is equal to F. P plus minus acting on PF is equal to F. And 3, there is a condition on the support of E plus minus F being contained in J plus minus of the support of F. Okay, so what does it mean in some picture? It means that I have some space-time where I have some function F which is supported here. So it has compact support, it's supported in a compact region of the manifold. And then if I act with one of these two operators, say with E plus, which is called the retarded green operator, then I have the support of E plus F here. And if I act with the advanced, I have the support of E minus F here. Okay? So I take a function, I act on it, and it gives me a function with support either to the future or to the past of the support of that function, where I acted on with these green operators. Okay? And they can be regarded as bidistributions, so namely what they're doing is they're acting on a smooth function of compact support, which can be viewed as a test function, and they're splitting another function. So if they would split a number, they would be a distribution, but because they split another function, we call them a bidistribution. Okay? Okay. Then, if these three conditions are hold, then we call these the advanced and retarded green operators of P. And what do we call P? Well, then P is called a green hyperbolic operator. P is called a green hyperbolic operator. In other words, it's a hyperbolic operator that has green functions, green operators. Okay. And there's a nice gadget that you can build out of it, which is called the advanced minus retarded causal propagator. So this is the causal. This is called the causal advanced minus retarded propagator. So far everything is classical field theory, right? Even if it has the word propagator, it doesn't mean it's a quantum object. Okay, it's a classical beast that appears in the theory of classical hyperbolic PDEs, right? And we can translate these points to see what the causal propagator, or the causal fundamental solution, some people call it like that, does. Well, first of all, you can solve the Klein-Warm equation by using it. So remember, if I act with E minus or E plus, it looks almost like an identity, right? So it spits out the same thing. But if I write it like this, E minus minus E plus acting on F, this is equal to F minus F, this is equal to 0. You can solve the Klein-Warm equation using this distinguished gentleman. I should say that these guys are unique. The advanced and the retarded are unique hence this guy is also unique by construction. It also satisfies that EPF equals 0, and it also satisfies, of course, a support condition, which is that the support of EF is in the union of the causal future and past of the support of F. Okay? So in other words, the support of EF will be all that, right? All the region inside those diagonals. And so this is very nice, because if somebody comes around and tells me, here's a PDE for you, and you say, but that's a normally hyperbolic operator. But I know that normally hyperbolic operators have, this distinguished advanced and retarded green operators, and I know that I can cook up the causal advanced minus retarded propagator, and so I know how to write solutions for that. Simply by acting with this guy on smooth functions of compact support, I can cook out a solution. Okay. Some green method for cooking out a solution like that. Okay? So now, having introduced those normally hyperbolic operators and those green hyperbolic operators, there's a little theorem, which is that every normally hyperbolic operator is green hyperbolic. Every normally hyperbolic operator is green hyperbolic, so every normally hyperbolic operator possesses this E plus, E minus, and this distinguished advanced minus retarded friend of ours. But there is, so this allows you to write solutions to say the Klein-Gordon equation or every equation that has that form. Notice, for example, that this theorem that we have just written, I'm not going to prove because we have no time whatsoever. But notice that this theorem that we have just written is completely irrelevant, for example, for the Dirac field. Because the Dirac operator is not of that form. It's a first order operator, it's not normally hyperbolic. So, this theorem, Dirac's equation couldn't care less. But there is a nice trick for writing also the green operators of the Dirac equation with the help of the Klein-Gordon ones. And so it is green hyperbolic without being normally hyperbolic. So this is really going only in one direction. If it is normally hyperbolic, then it is green hyperbolic. But it doesn't mean that if it's green hyperbolic, it has to be normally hyperbolic. Okay, so this is just one direction. This is going from normally to green, okay? Just making that little remark so you don't think that this whole construction doesn't work for anything but the Klein-Gordon field. It also works for the Dirac field and so on. Okay, so far everyone is more or less following the ideas? Pedro, more or less, yeah? Well, you should ask a question if you stop following, right? Okay, so every normally hyperbolic operator is green hyperbolic, and we know how to cook up solutions using this advanced minus retarded propagator acting on test functions, so smooth functions of compact support. We know that if we write EF, we get a solution. Particular, let me just stress that. For the Klein-Gordon equals 0, and I can write a solution like that. Okay. But there's a question, and the question to be asked is if every solution that we can write is of that form. That's a different matter. So it could be that we can write some solutions like that, but there are some other solutions that we can't get to by writing stuff in this form, okay? And there's a nice proposition that we can use for that, E equals P minus minus P plus, P advanced minus retarded. So this is the, by the way, this is the retarded because it's supported to the future, and this is the advanced because it's supported to the past, right? So just to establish notation. So the advanced minus, let E be the advanced minus retarded propagator of P, which is, of course, some green hyperbolic operator, right? Okay, then what do we have? First of all, the kernel of E is equal to P acting on smooth functions of compact support, i.e. over Pf such that F is in C not infinity. Okay. Secondly, and perhaps more interestingly for us, the image of E is equal to the kernel of P when viewed as an operator over spatially compact smooth functions, i.e. the kernel of P as operator on so the restriction to those functions, okay? The restriction to those functions, okay? And this is, the point 2 is very important because it says the image of E is equal to the kernel of P. The kernel of P characterizes the space of solutions, right? So remember, the kernel of P, namely P acting on something and making that something equal to 0, is solving the Klein-Gordon equation in our case. So if the image of E is equal to the kernel of P, it means that every solution I can write as E acting on something, right? So point 2 implies that every spatially compact solution of Klein-Gordon equation phi such that P equals 0 is of the form P F with F smooth function of compact support. Okay. Every solution to the Klein-Gordon equation that is spatially compact, which are the ones that we are concerned about since we started discussing this Klein-Gordon problem in arbitrary globally hyperbolic spacetimes, is of this form. So, you know, these green function techniques are not just only convenient, but they help you characterize the whole solution space in a covariant way, because these are really, these are really configurations, right? On-shell configurations of the problem, right? And this is, of course, very convenient for that thing that we wanted to do, which is to think of the space of solutions as the space of configurations in a covariant way, and then think of a phase space on it as functions going from this space of solutions to some numbers, say to real numbers if we're interested in the real Klein-Gordon fields. So, and then so this is very nice because we have the space of solutions. Now we just need maps from here to real numbers, and then we just need to put some Poisson bracket in that structure, right? So Poisson bracket in that space, right? And then we have the phase space, and we have constructed a covariant phase space for the theory. Okay. Right. So this means, in other words, going back to a previous description of the space of solutions in terms of initial data, that there is a one-to-one correspondence between these guys and initial data. There is a one-to-one correspondence between these guys and initial data. So if we can construct a phase space for this, right? We can for sure construct a phase space for that, and that's what we're going to do. Okay. Is everybody following the ideas? Yeah. Well, before anything, let me tell you what that looks like, expressed in some useful way. So what we mean by that is the following. We mean a field, phi of x, that solves, of course, the Klein-Gordon equation. And by this, we mean volume element integrate. We view this by distribution, as I told you before, and we integrate against the smooth function of complex support. And it takes, yeah, if you can work out some examples. For example, you can find what E is for the Klein-Gordon equation in Minkowski space. And then you can put a test function there, and you can prove that this is smooth. It's an exercise that you can do. But in general, it's true that this is going to be smooth. Right? This is just a general property. Okay, so this is what we mean by that. Right? And now I want to put a symplectic structure on the space of solutions. And to do that, it suffices to realize that this guy is antisymmetric. This E guy is antisymmetric. Right? How do we see that? Well, suppose that I want to write the following thing. Let's play a little game. By this notation, I mean take two functions of compact support, and I integrate them twice. Yes. And I integrate them twice, like that. How to How do I obviously see that it's antisymmetric? It's not obvious from that expression. But it is antisymmetric, let me tell you that much. It's antisymmetric. So so let me say that that's equal to equal G equal G prime M. X.
With a minus?
And if I switch, well, I've just relabeled.
Ah.
I've just relabeled. But if I switch these two, I get a minus sign. Okay. Maybe I have to write it in this advanced minus retarded way to see it, but yeah, let's just take it for granted that it's antisymmetric for now. It's also bilinear because if I just if I write f plus h here, I can distribute that in using linearity on each one of these entries, right? So it's antisymmetric and it's bilinear. And that's nice because it means I can use it as a symplectic structure on the space of solutions. So in what way? I can introduce a symplectic structure in the space of solutions. So for EF and EG, I call this, what's the right order? Yeah, G. Okay, so it's a bilinear antisymmetric. It's bilinear, it's antisymmetric, and it's non-degenerate as well. So namely, if some entry is 0 for every one in the other entry, then it means that that entry has to be 0. That's what it means. It's non-degenerate. Now I remember. Where does the antisymmetry come from? Well, the antisymmetry comes from the fact that these two guys are conjugate. So E plus and E minus are conjugate to each other. And if you use that property and play with it a little bit, then you can get the antisymmetry that I promised. So let's say that's an exercise. Okay. But that is the key that makes it antisymmetric. Okay. Okay, so now I have a space of solutions that carries a symplectic form, and in a similar way to the way that we did it in the first lecture, we can write the observables, so which are maps from the space of solutions to real numbers, and introduce a Poisson bracket on that space of observables with the aid of the symplectic structure. Okay, so observables go from some solution EF equals to EF to R. And I can identify them with smooth functions of compact support. So identify F for smooth functions of compact support. How do I do that? Well, I simply take the observable F of some solution EF to be the integral d to g and F. So I take a function of compact support, I integrate it against the solutions, and it comes down to this relation. So the solution is simply the integral in the prime variables of E against F. Against little f, I integrate it against a function of compact support f, and that gives me a real number. Okay, that gives me a real number, and this is an observable. So I can identify the space of observables with functions of compact support by integrating them against solutions. Okay. And now I would like to finally to finish my classical construction, the characterization of this classical space of solution and the covariant sense and of some covariant phase space of functions that take me from solutions to real numbers, I need to put a Poisson structure here. Okay? So I can try to do it. I can try to do it in the. I can try to keep exploiting my distinguished E, advanced minus retarded, and I can say that the Poisson structure here between two observables is equal to okay. Call that the Poisson bracket. There's one problem though, and the problem is that it is a degenerate Poisson bracket. So namely, consider the following smooth function of compact support. F equals PG, where G is in C, PATM. This is a Klein-Gordon operator acting on a smooth function of compact support, so it's a smooth function of compact support. And this is in the space of observables because I can map, right, from here to here. Okay. So if I write this, FG, I write it as a double integral. I'm going to ignore the measure and all that. But I can write it as P, G, E, F, right? G, sorry. So F is PG, I write it there. I integrate by parts twice, and I get G, P, A, G, E, G, which is equal to 0, because this is the field equation. This is the Klein-Gordon equation. Okay, so this is equal to 0. But it is 0 regardless what I put here. So for every G that I put here, for every smooth function of compact support, if I choose f of that form, it's going to be 0. So this is a degeneracy in the Poisson bracket, right? Because it should be 0 for every element only if this guy is 0. And it's not the case, okay? So what do we do? Well, we do what we do when we have these degeneracies, we quotient. Okay? So we call the real space of observables is quotient by C. Okay. So we identify all the functions that differ by P acting on a smooth function. Okay. If two functions differ by P acting on a smooth function, we identify them. So in particular, we can identify all the functions of this form with 0, right? And on this space, that Poisson bracket is fine, it's non-degenerate, and this is the space of observables. And now we have done the full characterization of the classical field theory, and maybe now it's a good time to take a 5-minute break before I'll do quantisation now, but let's meditate on this for a minute and then come back to it, okay? So we've done the full classical analysis. We have we've described in a covariant way the space of solutions and observables on the space of solutions, and we put a Poisson bracket that we have put a Poisson bracket in that space of observables, and that concludes the classical analysis. And now we can do quantization. And the nice thing about this is that since we have done everything covariantly, in the quantization what we will have is relations between covariant quantum fields, right? We will quantize these observables and we will get covariant quantum fields. In other words, we are not going to get the usual 3 field and 3 momentum in 4 dimensions, or n-1 field and n-1 momentum in n dimensions, but we will rather get the whole covariant observable, right? And we'll just do the quantization in the standard way, right? So we will promote observables to operators. We will make sure, as we will see algebra elements more generally, we will see that the generators of that algebra, so the fields, have to satisfy the Klein-Gordon equation, and we'll have some extra stuff like linearity, because this is a linear system, and we will have a reality condition, right? So first of all, quantization, we would call it going from observables to let's say fields, quantum fields, which are now going to live in an algebra. Okay. It also means that taking into account what we've just discussed about the degeneracy of the Poisson bracket in the naive sense, and how we have to quotient out some of these guys. If we have an observable G, which is equal to PG, it should go to PG equals 0. Should go to 0. The observable 0. Right? Then we would also like to preserve the linear structure, so a linearity condition. And finally, we have maybe some reality condition. There is some reality condition because it's a real scale. So this is our guiding map for quantization. We go from observables to fields, quantum fields. They're going to form an algebra, as we will see. Observables of this form should go to 0, because as we have seen, these are degeneracies of the Poisson bracket that we have to quotient out. We have some linear structure in the whole construction that we want to preserve, and we have a reality condition. And this is really all we need for defining what the Klein-Gordon algebra is. Okay. And it's literally just writing that with the dots and commas in the right place. Okay.
Benito, when you say a field, a quantum field, specifically the word field, you're thinking of, you said that we're going to belong to an algebra.
Yes.
When you say field, you're thinking like an algebra in every point of space-time? Or what do you mean with?
I'm thinking of an algebra associated to regions of space-time. You will see in a minute when I write it. I take space-time, I take the region of space-time. Take space-time here. That's it. Let's say this is space-time. I take a region here. This is M. This is a region O, and I associate to it an algebra. Okay. And it's not associated to every point because fields are distributional, right? Fields and quantum operators and so on are operator value distribution. So remember how we had in the canonical, in our canonical setting, we had something like this, right? And this is just the correct version of writing this distributional expression. Okay. This is a formal expression because the delta function is a distribution. This is a distribution. This is again distribution on the left-hand side. But the right-hand side, everything is suitably written. So namely, I smear this against some test functions, and I get these kind of. These are the real operators acting in Hilbert space. These are just formal expressions of those real. Thus, the actual operators are these are just formal expressions, right? The delta, you cannot simply put the delta function around them. I mean, you can if you know what you're doing, but it's a formal manipulation. And so what I mean in this context, the algebra of observables, when we associate it to a region, it will be smeared against functions supported in that region, maybe even the whole region. Okay? Compact region. Okay? But now I'm going to write the algebra of the whole space-time. And so I'm going to allow for the smearing functions to be smooth functions of compact support in space-time. Okay. Okay, so let mg glob heap globally hyperbolic. The real kind one algebra AM is a star algebra. That means it's an algebra that carries an evolution denoted by a star with identity, with an identity. So it has an identity generated. So I'm telling you now what the generators are by smeared fields. Smeared fields. Of what form? Of the following form, Pf, where F, well, it's generated by the smeared fields and the identity, of course, where F is a smooth function of compact support, and it satisfies what? Such that, and everything that we have written down there from intuition, we will carry to our definition. Such that F to F of F is linear, such that there's a reality condition, okay? And in addition, two relations. So one is saying that if I smear F against the test function of this sort, I get 0. So it's that condition that we have just written here. Okay? And this is a relation. In other words, it means that I'm identifying 0 with all the elements of this form. You should think of it as a relation. You should think of this as giving you a relation and forming an equivalence class of algebra elements. But for clarity, let's keep it like this. And finally, the commutator, which on the right-hand side uses the symplectic structure, like that. G here is also a smooth function. So this is what we have done before in the canonical setting. Now we're doing it covariantly. Right? Okay, good. So these two relations, these two are relations, which mean that you should identify this element with the unit with this proportionality factor, and that you should identify the zero element in this. And this is called the field equation axiom, and this is called the canonical commutation relation. So you can call them space-time commutation relations. Sometimes they're called like that. And this is called the field equation simply because of this. We write. So remember, we can use this. So what you all know what I mean by phi of f, right? I simply mean the integral of phi against f in space-time. Right. So what I mean by that is the integral in space-time that phi of t like that. And now if I use integration by parts twice on the box operator, what I get is the following. Okay. And there are no boundary terms because this is of compact support. But this is 0. This is 0. So this is 0. So what I'm getting is the field equation here. Okay. So the Klein-Gordon field satisfies the field equation. That's the statement of axiom 3, and that is coming very beautifully from this observation of the degeneracy of the Poisson bracket, right? So you see everything ties in very nicely. And this is just the commutation relation. It's anti-symmetric. This guy is anti-symmetric by the trick that I told you that you should do as an exercise. And it ties in very nicely with the this is exactly the equivalent version of that canonical version on a surface, right? It's exactly the same. Okay. So now that we have the field algebra, let me introduce you to states. We're going a bit quickly, so maybe you'll have to read your notes to really think about this. But let me introduce you to states. So definition, an algebraic state. So this is called an algebraic state. It's a linear functional. Which goes from the algebra to C, right? It's normalized such that it's normalized and it's positive, which I think positive is a very curious name for this property because it actually means not negative, okay? It's called the positivity property and it means not negative, okay? Furthermore, we define an algebraic state implicitly by telling me all the endpoint functions, and you'll see that I'm now using a very suggestive language defined by endpoint functions. So those of you who are familiar with field theory are now thinking, oh, why is he talking about endpoint functions now? So in other words, I take the algebra element product of n times the field, and I map it to a complex number, and I tell you what that is for every possible combination of endpoint functions. So n, so for 1, 2, 3, blah 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 point functions up to whatever you want, and in this way I define the states. Okay, I tell you, and because these are the generators of the algebra, if I tell you how they act here, I tell you how they act on every element of the algebra. Okay. Now, a very, very interesting class of states are called quasi-free states, and these are the ones that we will work with from now on. Quasi-free states. Quasi-free states are determined by the two-point function. Okay, determined only by 2-point function. Okay? So, only by this. If I tell you how they act on this combination, I tell you how they act for every algebra element. Okay?
That's also a definition.
That is a definition, quasi-free states. They're also called Gaussian. For example, people in quantum optics call quasi-free states Gaussian, because a Gaussian is determined sort of by the second momentum, first momentum, and that's it. Okay. And usually you can use the following nice formula, which you should take with a pinch of salt, but is good for getting all the endpoint functions when you have a quasi-free state. So if you expand this formula and check power by power, you can see how to write all the for example, the 4-point, you expand this to order 4, and you get a 4-point function here, and you see how to write the 4-point function in terms of 2-point functions by expanding this exponential on the other side. Okay, that's a nice formula that you have for quasi-free states.
It's like a big formula, no?
Yeah, that's right. Yeah, that's right. That is correct. Now, I'll tell you how to get back to the Hilbert space from this abstract setting. So now what we have so far for quantum field theory is we have some algebra with some elements. The algebra is generated by smeared fields that we want to identify with quantum fields of the quantum field theory. And we can make measurements of the algebra with states because they simply are maps from the algebra to complex numbers that we can get in a dial in some laboratory or something. And so far, there's no Hilbert space, there's no notion of positive frequency, nothing of the stuff that we talked about before is present in this discussion, okay? And so what I want to do in this last very bit, I won't get to states, I'll have to cover that tomorrow. What I want to do is to show you how to get back to the Hilbert space from this abstract construction. Let me just, before I go there, tell you a couple of things. So examples of quasi-free states are the vacuum. The vacuum state of a theory is a quasi-free state. And another example are thermal states, which maybe I'll touch on when we discuss black hole radiation and all that. Okay? So to get back to the Hilbert space, what you do is you do something called the GMS construction. And this construction is named after Gelfand, with an apostrophe here, Neymar, and Siegel. These are the guys that came up with this construction. Okay? And the point is you start out with an algebra and with a state on the algebra, and you cook up some triple, which is a Hilbert space with a dense subspace on it. I'll tell you what that is in a minute. In fact, a representation that allows me to take algebra elements and represent them as operators acting on that Hilbert space, and a vacuum state, So I start out with an algebra and with an algebraic state, and I want to cook up a Hilbert space, a representation that allows me to write algebra elements as operators, and a vacuum. Okay, this is the out, this is the in, and this is the out of that construction. Okay, and the point is, of course, that we can use the algebraic state to construct some inner product that will eventually become the inner product of the Hilbert space, and so on. Okay, so let me sketch the construction. So what we want to do, we want to construct an inner product using the algebraic state and the positivity axiom allows us to pretend to attempt to use it. There is of course a problem, and the problem is again that there might be algebra elements, there exist algebra elements, okay, such that and which are not necessarily the zero element. Okay, so we want to quotient them out. How do we do that? Well, okay. First step, consider the set. Okay. Of all algebra elements such that you have this condition that in a sense, the 2-point function, inverted commas, is 0. Okay. Then you realize that it's a left ideal. Realize, okay, I is a left ideal of the algebra. Okay. What it means is that if I take, let me tell you what that means. If I take an element of the ideal and an element of the algebra that is not necessarily in the ideal, okay, then their product in this order, so algebra element and an ideal element, is in the ideal. Okay? That's the definition of a left ideal. A right ideal is just switching the order of these two. Okay? So you realize that this guy is an ideal. You can do it. You can do it because you can use the Cauchy-Schwarz. So you can say, I know that this is 0. That's the condition that it's in the ideal. And now I want to show that BA star BA is 0. Okay. And the way to do this is to rearrange that, use the Cauchy-Schwarz inequality. So just so you remember what the Cauchy-Schwarz inequality is. And the game is that you will find that this is equal to WA star A times something, but WA star A is 0, therefore this is 0. Okay, so this is the, sorry, this is going to be less or equal to W star A something times something. And you know that this is 0, so this is 0. Okay. Using the Cauchy-Schwarz inequality. Okay. That's the trick to see that that's an ideal. Now, step number 2. step number 2 is to quotient the algebra by that ideal and define this friend dw. And dw, as you can see, is this guy. We will see in a minute why it is that guy. Well, it turns out that if you quotient by the ideal, there's no obstruction anymore for you to making this an inner product. So on dw, I'm calling the quotient elements with this bracket, meaning equivalent relation with respect to that quotient. Then this is an inner product, that space. And this is the inner product that way. So it is linear, it's also, so it's linear here and here. It's linear here and perhaps antilinear there. It's positive definite because, well, because of positivity. And I think that's what we want, right? And okay, third point, complete with respect to this, and we call the completion is the Hilbert space. Okay, so what does it mean now for, I mean, the completion simply means you take Cauchy sequences here and you add the limiting points. That's all it means. And you call the completion H, the Hilbert space. And by construction, this is dense in the Hilbert space because it's some space being dense simply means that every element of the Hilbert space is either here or it's a limit from points here. Okay, so that means dense, and by construction, because this is just simply adding a few limiting points, by construction this is dense here. Okay. 4. Okay. Define a map in this way. So, in other words, we define a map from algebra elements to linear operators acting on the dense subspace of H. And we need to act on the dense subspace because the algebra, this is a technical point I'm going to gloss over. The algebra fields is unbounded. They're unbounded operators. If they were bounded operators, then this would be equal to that, and this would act on the whole space. It doesn't matter. Okay, we don't need to. Just a technical point. And I define the action. I define the action of one of these algebra elements on a Hilbert space vector simply in the following way. Okay, simply in the following way. This is a vector. This is a vector here. Okay. This is an element here. And this is a vector again. This is how the algebra elements act as operators. And finally, realize the image of the state under some algebra element as some expectation value, right? Using that where the identity is identified with the vacuum state. And let me just say a few things about this. This is called a representation, and it has to satisfy several properties. For example, it has to send the identity to the identity operator. It has to be homo, so namely has to satisfy that. Has to be linear, and it has to preserve the star of the algebra by the Hilbert space conjugation star. Okay. Right. So finally, let me introduce some notation just so that you feel more at ease, perhaps. I'm going to call this an operator on a Hilbert space. It's just some notation. And I'm going to write it as where EF is a solution to the field equation and K is just K is known as a K-map. It was invented by Bernard K, conveniently, so he called it K. And I'm not sure if it's called a K-map as in letter K-map or a K-map as in his name map. It's called a K-map, and it maps solutions, classical solutions, to vectors in the one-particle Hilbert space, so to vectors. So K goes from the solutions to one particle Hilbert space. And finally, the Fock space of the theory is obtained by acting with all these endpoints on the vacuum. Okay? And that will give me all the elements of the Fock space. Okay. By this I mean I represent every algebra element, namely phi times phi, phi times phi times phi, blah blah blah, and I act on the vacuum, and this gives me the Fock space of the theory. By the way, this, just so to give you some notation, this is called the one-particle structure. One-particle structure with respect to the state omega. Just a piece of notation. The K-map on the one-particle Hilbert space is known as a one-particle structure with respect to the state omega. And by the way, we've finished the construction, right? We have completed the GNS construction, and we now know how to go from that abstract setting of algebras and algebraic states to concrete operators on a Hilbert space, concrete operators on a Hilbert space. I've just sketched the GNS construction, and maybe you want to, of course there are many details that I glossed over, but this is the main idea of it. Okay? And I think we should wrap it up now, because we just have 9 minutes. So let me just, in 2 minutes, tell you what we're going to do next. So next time I'm going to look at states. We're going to look at states. Okay, let's look at states. So in particular, in the whole construction that we've okay, we're going to look at states. We're going to see that we're going to realize that states, especially quasi-free states, is useful to think of them as defined by the two-point function, as I said, and to view the two-point function as a bidistribution. And when you do that, you can look at the distributional singularities of this bidistribution. And when the singular structure of of this bidistribution is of a certain type, which is the exact type that is obtained by analyzing the singularity structure of the Minkowski vacuum. So when any other state has the same singularity structure than the Minkowski vacuum in its two-point function viewed as a distribution, then we call this state Habermas, and this is a good physical state that we can use to renormalize the stress energy tensor and renormalize other observables that are not in this field algebra of linear observables. So for example, if we wanted to look at the vacuum polarization, which is something like phi squared, yeah, if we wanted to look at the expectation value of that, then this state should better be Hadamard for this to make sense. If we want to look at the expectation value of something like the renormalized stress energy tensor, then this guy should be Hadamard for it to make sense. Okay. So this is a very important property in curved space-time quantum field theory, but it's also a very important property in flat space-time quantum field theory because it establishes in which sense the Minkowski vacuum is a good vacuum, and other vacuums that you can put in flat space-time, like the Rindler-Fulling or Fulling-Rindler vacuum that we constructed in the second lecture, is also a good vacuum. Okay? And I'll leave it there for today. Okay, so next time we look at states, and I'll try to be quick and cover some applications. All right? Okay, thanks. And thanks to Ricardo.